in exercise 14H, you're going to have a look at simply an observation, which then leads us to, I guess, a property that allows you to do a particular calculation. Now, that probably is not making much sense, so let's have a look at what we're talking about. So there's a few things. We're talking about very small angles, very small. So an angle not much bigger than 0 degrees, something very, very small. This only works in that case when the angle is very, very small. So you know that we often talk about sine of x. So if x is very, very small, you can see here in the notes that mathematically another way of writing when x is very, very small is we find the limit as x is approaching 0. Now, we've looked at limits previously, x approaching 0 or x approaching infinity, and you know how to do calculations to find the limit. The questions that you'll come across here are very much similar to those. You can see down here we're looking for the limit as b approaches 0. So what you've got to recognise within that question is, this is a question about the very small angles. Now we know that often we can just substitute the value that the pronumeral is approaching. In this case we can't because we'd have a 0 in the denominator, so we have to use some other understanding of what's going on there. Now, before we can do that, we need to do a bit of investigating. Remember I said this is clearly an observation. The property came out of observations. So the other thing to be really aware of is you must measure your angles in radians. This doesn't work with degrees. You measure the angles in radians. So if you take your calculator and make sure it's in radians and find for me the sine of 0.02. So just in case, I'll just delete that. Just in case you're unsure about how to get to radians, we've got degrees radians here just above the answer key. Anything written in yellow, we need to press second function. And you can see we want to select 2 now, and our calculator is in radians. And as you can see here, you get 0.019986. If we were to round that to 2dp, then we would get 0.02. Now you can try that for many other small numbers, and what we know happens is that the sine of x actually ends up being this x, and of course that's all provided it is in radians. So when x is very small, the sine of x is x. Okay, and that's what's actually written here. What we know by observation, and it only works for small angles measured in radians, is that the sine of x is approximately equal to x. Let's have a look at the application of that. So, like it says here, we get this property that the limit as x is getting very, very small, the sine of x on x would actually be 1, because what could we replace sine x with? We could replace it with x, and x on x is 1. Now, you can see up here in the BLAST it says, although this is a 2-unit concept, it is frequently tested in Extension 1. It doesn't mean it won't come up in Advanced, but it's almost always somewhere in the Extension 1 exam. There's a similar observation when we look at tan of a very, very small number. And as you can see there on the calculator, that tan of 0.003 radians is 0.003000. That's close enough for us to again say that the tan of x, well, this was 0.00300 blah, and the tan of x is actually x, which leads us to our second property. As x becomes very, very small, if you can set it up such that you've got tan of x over x, you can replace the whole of that with 1. Now, you have to have tan of x over x. These x's have to be exactly the same things. So the moment that we've got, say, for example, a 3x in there, we would need a 3x in the denominator. We know that we can't take 3 out of tan of 3x. We cannot take it out. So the only way we could get that situation set up here is to introduce a 3 into the denominator. It's likewise with sine. If you had sine of 5x, you would need to have a 5x in the denominator. You cannot take 5 out of sine 5x. There's no rule in trig that allows us to disassociate the 5 and the x if it's written that way. There are ways in which we could introduce a 5 into the denominator. You've seen that before, and you're going to see those sorts of situations. So, things to realise, that this x, the terms in those two positions must be identical. Just before we go on, let's have a look at cos of something very, very small. And you can see a very different observation now. The cos of a very, very small angle is actually 1. Now, if you had thought about the the cosine curve, if you thought about cosine, here where theta is very, very small, of course cosine is up here at 1. So as we're approaching 0, very small angles, the cos is actually 1. That doesn't lead us to this same observation or property involving cos like this, but we do know that the cos of a very small angle would be 1. Okay, so let's try these examples. Limit as b is getting very small of sine b on b is going to be, as long as these two values are identical, doesn't matter what they are, and it's heading towards 0, the answer is 1. The limit as x tends to 0, and again we've got these two values being identical, the tan of something over itself is also equal to 1. Doesn't matter whether this angle is a fraction, as theta is approaching 0, so this is going to go to 0, this is going to go to 0, but we know that sine of an angle over itself is equal to 1. So, let's have a look at this next one. We don't actually have these two items exactly the same. We can't just pop a 3 in there, we can't insert a 3 in there. So all we can do is remove that 3. So you can see that 3, I guess what it would have looked like is the limit as x is approaching 0 of 1/3 sine x on x, because 1 times sine x is that sine x, and 3 times x is that 3x. You can see that I've separated the 1/3 out. Now, because 1/3 doesn't rely on x at all, 1/3 is stuck, we can take the 1/3 out the front and only consider the x component of the limit, and we've nicely now got sine x on x, which we know goes to 1, so we've got 1/3 times 1, which is 1/3. It's saying here the limit as x approaches 0 of sine 2x on x. We cannot, that's a cannot, is not equal to 2. We cannot take the 2 out of that position. So with that in mind, we have to think about how we could get a 2 into the denominator. If we want to introduce a 2 into the denominator, we don't want to change the size of any of this, so we introduce 1 in the form 2 on 2. So that then gives us the option of taking this 2 right out the front. So we'll have 2 times the limit as x approaches 0, because we don't want that in there anywhere. But it does allow us then to write sine 2x and keep that 2 inside. We know that this component of the calculation would go to 1, and again 2 times 1 is 2. I thought this was a bit of a different take on the property. I really liked this question. Explain why the sine of 2 degrees is approximately pi on 90. So 2 degrees we know is small. 2 degrees in radians would be 2 times pi on 180 radians, which is pi on 90. And if we've got the sine of a small angle, what we know is that sine of pi on 90, which would be approximately sine is 0.03, so we're definitely taking the sine of a small angle, 3, 4, and we know that by definition the sine of a small angle is approximately equal to 0.34, which is this pi on 90. See how you go with exercise 14F.